In this video, we'll be talking about absolute versus conditional convergence. So in all the examples that we've been currently going through, we've been talking about the concept of conditional convergence. We've been kind of ignoring what absolute convergence is, or we haven't really been talking about it. But from this point forward, when we see a alternating series, or a series that has a -1 k to the power of something, we can now start talking about absolute convergence and conditional convergence. Now, in most cases, this particular setup, the question will be asked in such a way of, is the following series absolutely convergent, conditionally convergent, or simply divergent? Now, the reason why they say it this way, or they phrase it this way, or they ask it this way, I should say, is specifically because there are levels now to convergency. So our first definition is when is something absolutely convergent? So we can say that the summation a sub k is absolutely convergent when the series of the absolute value of that same exact thing is convergent. So now this is actually a more stringent or restricting rule. Now, it kind of opens up the series a little bit more, allows us to ignore some details of the series, but it is, again, very specific that I need the absolute value of the series to be convergent for us to state that we have absolute convergence. Now, otherwise, if the series a sub k is convergent, again, if we just look at it and it happens to be convergent all on its own, then we can say it is conditionally convergent. Now, it's important to note that it's conditionally convergent if it's not absolutely convergent. So technically we have absolutely convergent, we have conditionally convergent, and then we kind of bypass those two statements in a number of other examples that we've already done, and we just say that the series is convergent. We ignore that it's conditionally convergent. We weren't asked whether or not it was absolutely convergent, so we don't care if it's absolutely convergent. We just kind of talk about convergency in and of itself. So again, if the question just says is it convergent, you can use absolute convergence to imply convergence. Again, you can use absolute convergence to imply convergence. If we're asked about conditionally convergent, we actually have to prove that it's not absolutely convergent, but the series without the absolute value is convergent. So again, it's kind of layered. You have absolute convergence implies regular convergence. Okay, absolute convergence implies regular convergence. If absolute convergence fails, but we do have that it is convergent in and of itself, this implies conditionally convergent. Now, it is also important to note that there's one extra layer, and that layer is whether or not the series is divergent. So back up here, if this thing right here isn't convergent, if the summation of the absolute value of a sub k is divergent, that means nothing about the series of a sub k, other than it's not absolutely convergent. So if we get divergent with the absolute value, and then we come to the regular function and we get divergent with that one, then we can say that the overall series is divergent. But if I don't go that extra step, if I end up concluding based on the absolute value convergency, if I test this and say, well, this thing is divergent, so this thing is, that's not necessarily true. Again, this only holds on convergent series. Divergency does not work. Now, it does work backwards. If I have the original series, a sub k is divergent, this does imply then also that it is not absolutely convergent. Because again, it has to be convergent in any way for it to even be possibly absolutely convergent. So again, the layer is absolute convergence implies convergency. If it's not absolutely convergent, it can be conditionally convergent. If we're not asked about convergency or absolute or conditional at all, we can just simply test the function to determine if it's convergent. We will not specify conditional, we will just simply say it's convergent. If, however, we can't prove absolute convergence and we end up proving that it's not conditionally convergent, we then make the end conclusion that it's divergent. Now, with all this being said, we're still going to go ahead and start with basic rules of testing convergencies. We can, in most cases, start by testing the original function on whether or not it's divergent. If I can prove that the original series is divergent, then I'm done with the problem. It's not absolute, it's not conditional, it's simply divergent. However, if I can't conclude that this thing is outright divergent, well then it might be better for me to jump back over to here and start here and prove that this thing is convergent. If I can prove that this thing is convergent, then this thing is also convergent and I don't have to worry about that. But if I get divergence on this and I have difficulty proving divergence on this, then I'm really going to have to either find a way to prove divergency or prove that it is convergent. So again, we have layering now of determining whether or not it's something convergent, but it's a matter of identifying which level we want to start at and how to determine whether or not we have absolute convergence, conditionally convergent, or divergent in and of itself.